The night sky is full of stars, galaxies, planets, and asteroids. Asteroid actually means star-like. Even in the very best telescopes, they look like nothing more than just points of light in the sky. They're cosmic boulders, and there are trillions of them. From the size of a car to giants hundreds of miles across, together they tell the story of how we came to be. The Earth was made by asteroids 4.5 billion years ago. The solar system is a vast cosmic whirlpool. Dust sticks together to create asteroids. In our own solar system, and in every solar system, the first objects to form, the first large rocks before planets form, are essentially asteroids. There are no planets yet. Instead, trillions of rocks and stones swirl around the newly born sun. It would have been a very strange place, kind of like a merry-go-round of all these objects orbiting around the sun. And there are millions of these asteroids, just in different sizes and different shapes. These ancient asteroids will shape the solar system and build the planet we live on. Asteroids are so much more than just rocks in space. They're the building blocks of our very own planet. Billions of small asteroids must clump together to make a planet. But asteroids move at thousands of miles per hour. Getting them to stick is hard. We're here at the stock car race to see what the early solar system may have looked like. High-speed car collisions cause damage. Parts smash off. Asteroid collisions are the same. To join together, somehow they must collide and stick. Stock cars show how this happens. They move fast, but all in the same direction, just like the asteroids in the early solar system. When collisions happen, they're relatively gentle. Instead of smashing apart, they join together. These are planets in the making. They're going around almost at the same speed and they begin to stick together. And that's how planets begin to form. Asteroids gather into rock piles, like two cars locked together. As more asteroids collide, the rock piles grow. Building whole planets this way would take billions of years. Yet the planets formed in just a few million years. How? When the rock piles reach mountain size, gravity speeds up the process. Gravity started to become important when they were about the size of one of the Rocky Mountains, like Pikes Peak behind me. It was when they were several miles across that they had enough mass that their gravity could start to draw material in. Now, if the Earth weren't here and it were just Pikes Peak over there a few miles away, I would very slowly start to drift toward it, faster and faster, accelerating the whole way until I actually impacted it. The gravity would draw me in. It would pull on me until I actually hit the mountain itself. Large asteroids are mountains in space. The early solar system is full of them. Their gravity pulls other asteroids toward them. The larger an asteroid becomes, the more rocks it pulls in, and the faster it grows. At that point, the events happened very quickly. It would actually draw that stuff in and grow very rapidly. One of these early space mountains keeps on growing until there are no rocks left to pull in. It's no longer an asteroid. It's a young planet. The Earth, all of the planets, even the Earth, they owe their existence to the fact that there were asteroids back then. This is how all rocky planets form. Asteroids join together until there are no more left. Mercury, Venus, Earth, and Mars are all overgrown asteroids. But beyond Mars, something went wrong. No rocky planets. Instead, billions of rocks and boulders that never joined together. The asteroid belt. Out here, construction came to a halt before a rocky planet could form because of Jupiter. The gas giant had already formed nearby. Jupiter is humongous. It's the 800-pound gorilla. It dominates everything gravitationally. 4.5 billion years ago, Jupiter's gravity causes havoc. It flings asteroids in every direction. Giant boulders scatter from their regular orbits onto extreme chaotic paths. The stock car race ends, and the demolition derby begins. Once Jupiter got involved, the solar system began to look like a demolition derby. Things colliding with each other, going in all sorts of different directions. A cosmic pileup. Rocks smash into each other from every direction. Violent, chaotic collisions. These rocks don't clump together. They shatter and create the asteroid belt. Violent collisions still rock the asteroid belt today. In 2010, the Hubble Space Telescope captured this. The aftermath of a hypervelocity collision. Asteroids can both create and destroy. If many of them come together gently, you get planets. Too much violence, and you get the asteroid belt. Billions of rocks and boulders. A graveyard for a planet that never formed. The asteroid belt is a mysterious realm full of danger and full of promise. A new frontier just waiting to be explored. Asteroids are as diverse as planets or moons. Some are metallic, some rocky, some icy, some even have their own moons. They come in all shapes and sizes, from boulders all the way to miniature worlds. And they're everywhere. Distant solar systems have their own asteroid belts. The star Epsilon Eridani is just 10 light-years away. It is not one, but two asteroid belts. Another star has a belt 25 times larger than our own. If you're actually living on a planet in that solar system, the asteroid belt would look much brighter than the Milky Way, a big streak across the night sky. Asteroid belts are the scraps left over after planets have formed. So they tell us a lot about their solar system. Our asteroid belt is full of variety. Millions of strange asteroids, each with a story to tell. Yet we have barely explored it at all. That's about to change. The first mission to the asteroid belt is underway. The Dawn probe. Its goal? To explore a mysterious distant realm. We're going to learn more about the main belt asteroids from this one mission than we have since we discovered the asteroid belt in the first place. In July 2011, Dawn arrived at its first target and sent back these pictures. Vesta is the second largest asteroid in the belt. It almost became a planet, then Jupiter's massive gravity stunted its growth. Today, it's a miniature world. One of the common misconceptions about the asteroid belt is that things are fairly small. But some of the largest asteroids are really more correctly thought of as minor planets. They're several hundred miles across. Vesta even has a mountain 3 times higher than Everest. Mark Sykes is co-investigator of the mission. It's just a real excitement because you're seeing a new world for the first time. And you know just enough to be dangerous and trying to explain what it is that you're seeing. Vesta is like a snapshot of the infant. Earth when it was just as wide as Arizona. We're seeing perhaps what an embryonic early terrestrial planet like Earth looked like in the first few million years of its history. The Dawn probe has already found that Vesta has an iron core, like the Earth. Evidence that the Earth's core formed when the planet was still young. This stunted world offers us a window on the Earth's distant past. We're seeing things that we didn't necessarily expect, but that's what makes it fun. After Vesta, the Dawn mission will head into the asteroid belt's outer reaches to explore an icy primeval world 4 times bigger than Vesta. There, Dawn aims to settle another mystery about the Earth's past. Where did our oceans come from? The asteroid belt is ancient, violent, and remote hundreds of millions of miles from Earth. But not all asteroids stay in the asteroid belt. They can roam all over the solar system. The moon's surface records a violent past a massive cosmic bombardment. We see evidence every night when the moon comes out. What do we see? A pockmarked barren world evidence that there was an intense rain of asteroids and debris. That came from outer space, completely disfiguring the surface of the moon. Millions of craters cover the moon, including the largest in the solar system, 500 miles across, itself scarred by thousands of smaller craters. A storm of asteroids blasted the moon 4 billion years ago. And if that happened to the moon, it must also have happened to Earth. The Earth is a much bigger, more massive target in space. For every one of those craters you see on the moon, you've got to imagine 50 or 60 craters here on the planet Earth. The impacts back then must have been horrendous. Every few weeks, a gigantic object hurling from outer space, gouging out a huge chunk of the planet Earth. We call it the Late Heavy Bombardment. For 200 million years, fireballs rained from the sky. The impacts triggered earthquakes bigger than any in recorded history. 10,000 miles per hour. Hurricanes ripped through Earth's primitive atmosphere. But asteroids also bring a new substance to Earth. Some asteroids contain ice-frozen water that melts on impact. Each asteroid brings a little more. But could asteroids really bring enough water to cover 2/3 of our planet? One of the questions we have is, how did water get to the Earth? Because the original Earth, we think, was very hot and very dry. NASA's Dawn probe aims to find out. The asteroid belt still contains icy asteroids to this day, in the coldest, most distant part. In 2015, Dawn will arrive at the solar system's largest asteroid, Ceres. Ceres is 1/3 the mass of the entire asteroid belt and 4 times as large as any other known asteroid. A lot of it looks like pure ice. Ceres has a rocky interior, an ice-rich mantle. It's far enough away from the Sun it's cold enough that it's stable. Ceres is just 600 miles wide. Yet there may be more frozen water here than all the fresh water on Earth. The Dawn mission will find out for sure. If Ceres really does hold so much ice, it could help explain why the Earth has so much water. When asteroids bombarded the Earth 4 billion years ago, massive icy bodies like Ceres could have brought vast amounts of water. Water itself, in the form of ice, came down from the heavens to create the lush oceans of the Earth. And not just the oceans. Clouds, rivers, glaciers may all have come from space. The Dawn mission may uncover something even more significant on Ceres. It may find an ocean underneath the ice, an inner mantle of liquid water, melted by heat from the dwarf planet's core. Life as we know it depends on water. Wherever we find water, we may find the spark of life. If there is a liquid water ocean underneath the surface today, that begs the question of whether there could be life there. Extraterrestrial life could have started in the asteroid belt. Ceres could be home to basic life forms flourishing in a subsurface ocean. If asteroids like Ceres can support life, that could reveal how life started on Earth. 4 billion years ago, asteroids bombarded the young Earth. They brought water, and they may have brought life from the asteroid belt to Earth's new oceans. Primitive organisms that thrived, and ultimately evolved into all the Earth's creatures. A planet that brims with life. Our earliest ancestors may have arrived from the asteroid belt. Perhaps these little worlds could be incubators of life throughout our solar system, maybe even in other solar systems around other stars. Asteroids may bring life to worlds throughout the universe. They may also bring death. Asteroids are crucial to life in the universe. But once life gets started, asteroids can also end it. Asteroids really have 2 sides to them. They're sort of creation and destruction, all wrapped up together. Planet Earth is right in the firing line. We've come to realize in recent years that we live in this kind of cosmic shooting gallery. Astronauts witnessed this firsthand. When I flew on Apollo 9 and I went outside the spacecraft, it's very likely that I was hit by, very, very small asteroid. And it will make a hole in a spacesuit. So the suits are very, very well built. The result of which is they're very heavy. But we've never had one penetrated yet. The Earth, too, has built-in protection from small asteroids. The atmosphere. When asteroids hit the atmosphere, they burn. I can remember one night when we were looking down at the dark Earth, and I kept thinking I saw an occasional flash of light, but I wasn't sure. And then suddenly we're realizing, of course, we're looking at shooting stars. Most people don't realize that in a given night, if you lie in the grass and look up at the night sky, you'll see shooting stars, many of them, each hour. Most shooting stars are the size of grains of sand. These burn up, but larger space rocks can punch right through to the ground. Here's the proof. Meteor crater in Arizona gouged out by an asteroid just 150 feet across. You can see the huge force that excavated this. And you can also see the layers of material that were turned over as the crater was excavated. And so, some of these rocks around here are kind of upside down from where they started. There have been millions of impacts like this in Earth's past. There will be more. Imagine a city where Meteor Crater is now. They'd see a fireball coming through the sky very quickly. This thing is moving at 8 miles a second. And so it wouldn't take very long for it to move across the sky and strike the ground. Heat from the fireball scorches the surface. But most damage comes after the impact. Once it strikes the ground, this takes a few seconds to create, so very short time, very large amount of energy, and very devastating effects. The asteroid is obliterated. A mighty shockwave generates winds, 6 times more powerful than a hurricane. You have the blast that comes out probably for several miles, and large debris that would crush buildings and homes. If it hit today, the asteroid from Meteor Crater would be a city killer. But the Meteor Crater asteroid was small. It was likely a fragment from a much larger asteroid. Whatever it is that hit Meteor Crater wasn't very big. It was probably 50 yards across. So, not even as big as a football field. There are millions of much larger asteroids. These would cause even more carnage, country killers, and worse. Asteroids over a half-mile wide could end our civilization. Worldwide killers. We know, because it happened already. There are traces everywhere. There's evidence of giant impacts all over the world, and it's right underneath your feet. And in fact, in some places, it's pretty easy to spot, like here in southern Colorado. So this layer of light-colored rock, that's the KT boundary. It's called a boundary because it marks the boundary between 2 different time periods. Everything that was put down here, underneath the KT boundary, had dinosaurs in it. Everything above it, no dinosaurs. So it really marks that point in time when the dinosaurs went away. The layer is rich in an element called iridium. It's rare on the Earth's surface, but common in asteroids. So if a giant asteroid came in, smacked into the Earth, blew out dust everywhere, the iridium inside the asteroid would have settled down into a layer all over the Earth. And that's exactly what we see right here. The clear fingerprint of an asteroid. There must have been some perfect morning before the asteroid impact, when the land of the dinosaurs was still very much as it had been for millions of years. Then there would be something sighted up in the sky, something very bright, very hot. The asteroid is 6 miles long, big enough to devastate the planet. The asteroid that came in and formed this layer here was very massive and was moving very fast. And so when it impacted the Earth, that energy was turned into, boom, very, very big boom. It has the force of 5 billion Hiroshima bombs. Large pieces of Earth blow out into space, then rain back down. A storm of fireballs. Wildfires rage across the globe. In the KT boundary layer is a layer of soot, and that's an indication that there were global fires. That everything on Earth was basically on fire after this happened. The Earth plunges into darkness. An impact winter. Mass extinction. Basically, you can think of this as every environmental catastrophe all happening at the same time. It was an incredibly bad day for planet Earth. A chilling reminder of the threat from space. Asteroids this big will hit us again. We will go the way of the dinosaurs. We will be survived, most likely, by the bugs, the cockroaches. They will be the ones who will inherit this Earth. But hopefully that's going to be a long time from now. Is mankind doomed? Or can we dodge fate? Asteroids built our world. They brought water. They killed the dinosaurs and made room for new species. But asteroids are also a threat. We know absolutely for certain that there will be large impacts in the future. So it's not a question of if, it's only a question of when. Large meteor impacts happen once every 60 to 100 million years. We're due for one soon, perhaps. If we want to survive, we need to prepare. We must find the asteroids, determine if they're heading for Earth, and stop them. That's not easy, but it may be possible. Happily, there's a difference between us and dinosaurs. We have telescopes, and we can get advance notice of an impact. Asteroids are much smaller than stars and planets. It's hard to see them coming. To track asteroids, you need a giant telescope, like the Arecibo Observatory in Puerto Rico. Right now, I'm on top of the largest telescope in the world. And this place may actually be our best defense against getting hit by one of these near-Earth asteroids. The vast bowl is 1,000 feet across. And it's not only the world's biggest telescope, it's also the world's biggest radar dish. When you think about using radar to keep track of all the airplanes that are up in the sky, well, this one is so powerful, it can actually track near-Earth objects millions of miles away. Unlike a telescope, radar can directly measure an object's distance and reveal exactly where it is. That's perfect for tracking asteroids. In 2004, astronomers spot a stadium-sized asteroid heading toward Earth. Its name, Apophis, after the Egyptian god of destruction. The day it might hit us? April 13th, 2029. Friday the 13th. Apophis was the first near-Earth object of the modern era. That had astronomers honestly scared. There seemed to be a 1 in 30 chance of something catastrophic happening. Arecibo springs into action against the biggest threat from space ever detected. Apophis could devastate entire countries. But the asteroid's path is still uncertain. It might hit her, it might just miss. Only Arecibo can tell us for sure. The Arecibo telescope was able to reduce the uncertainty of Apophis by 98%. It told us that there was no chance this thing would hit us in 2029. It will be close. Apophis will pass closer to the Earth than the Moon closer, even than some communication satellites. We have powerful tools to detect asteroids. Someday we'll find one that will hit the Earth. How can we protect ourselves? The obvious strategy is to destroy the asteroid before it destroys us. But that could be risky. You don't want to blow it up because you may end up breaking it into 2 or 3 or 5 pieces, which then end up hitting all around the Earth and wiping out many, many people. Exploding an asteroid could cause more harm than good. Better to make it miss completely. When an asteroid is headed for Earth, their future paths cross, and they'll both reach that point at the same time. Imagine the Earth is a freight train, and the asteroid is a car both heading for a railroad crossing. If they reach that crossing at the same time, they will collide. The best way to avoid the impact is not to swerve away from the train. It's to hit the gas or the brakes. If you can cross the tracks before the train gets there, or wait for the train to pass and then cross them, that's what we want to do with asteroids. Just to make sure that the asteroid and the Earth aren't at the same place at the same time, by simply slowing down the car, we're going to miss. That's the way to avert a collision. But asteroids don't come with brakes. We need another way to change their speed. One approach is to use the asteroid's gravity. For a small enough asteroid, all you need to do is park a large spacecraft next to the asteroid. A spaceship would hover above the asteroid's surface. You can thrust with your spacecraft to keep it from falling onto the surface of the asteroid. And so, it's like a little gravity tractor using gravity as the tow line to move the asteroid out of the way. Over time, the gravity between them would slow down the asteroid just enough for it to miss the Earth. Asteroids could shape our future in another way. We could turn them from a deadly threat into a precious resource. Asteroids are a creative force. They build planets, they bring water, but they're also destructive. Asteroids are both a boon and a threat. Early on, they bring the materials for life. Later on, they can destroy life. Asteroids bring violence and death, but life may not always be in danger. Ultimately, if life becomes intelligent enough, it could send objects out to deflect or destroy the impending asteroids. We now have the technology to divert asteroids. That means we can treat them not as a threat, but an opportunity. We could mine them. Many of them are just ripe for the taking in these wonderful mineral resources. And so the asteroids in some ways are literally gold mines in the sky. They're not just gold mines, they're zinc mines, aluminum mines, platinum mines. Just one average-sized asteroid could contain minerals worth thousands of billions of dollars. But first, we have to reach the asteroids. On April 15, 2010, President Obama announced a new plan. By 2025, we expect new spacecraft designed for long journeys to allow us to begin the first ever crewed missions beyond the moon into deep space. We'll start by sending astronauts to an asteroid for the first time in history. Ironically, the easiest asteroids to reach are the same ones that threaten the Earth. As they pass by, a spaceship could rendezvous with the asteroid. Yet, even when asteroids come so close, asteroid mining may be too good to be true. The reason why we're not mining the asteroid belt today and letting the space program pay for itself is because of cost. It takes an enormous amount of rocket fuel and expertise to bring back an asteroid from outer space. But perhaps we don't need to bring the minerals back to Earth. We could use the resources of asteroids to build settlements out in space. You don't have to build a space station. It's already there. You don't need shielding, because you can simply drill right into the soil and use the rocky material as shielding against radiation and micrometeorites. So, in some sense, think of an asteroid as a ready-made space station. Low gravity makes it easy to come and go. There's plenty of water and all the construction materials that colonizers could ever need. So one day, when we have colonies in the asteroid belt, and we need to build cities there, that's where we're going to find valuable deposits of metals. In the asteroid belt itself. A vast band of cities in space strung across 1 billion miles. And not just cities, but factories, to turn metal from the asteroids into spaceships. Perhaps asteroids could actually provide the metal, the real structure to build our spacecraft. So, somewhere up there between Mars and Jupiter, there may be the makings of our future spaceships. Ultimately, asteroids may be a stepping stone, by which we can one day leave the entire solar system. Asteroids made the Earth. Perhaps they even brought life here. And in the future, asteroids could help humans escape the Earth and colonize the galaxy. So, in a way, asteroids are drawing us out into space, whether to protect ourselves or to expand where we live. Our planet is extraordinary. It provides everything life needs. Trillions of creatures, plants, and us. Well, you look down at the Earth from space, and everything that we know of that's life is down there on that planet. That beautiful planet that you now are going around every hour and a half. And that's almost overwhelming. Just the beauty of the Earth. It's unique in our solar system. But is it unique in the universe? It's important for us to understand the conditions that led to the formation of the Earth, because then we can look for those conditions around other stars. And if we find those conditions there, then that would suggest that other Earths could be forming elsewhere in the universe. Could there be other planets like ours among the stars? To find out, we must travel back in time and discover how the Earth was made. Rewind the clock 4.5 billion years, and this is what you see. This speck of dust will become the Earth. By combining with countless others, they're all part of a giant cloud called a stellar nursery. The first step of planetary formation is about to start. An event that will transform the cloud into thousands of infant solar systems, including our own. The same process is happening today, 7,000 light-years away in the Eagle Nebula. Our own solar system formed inside clouds of gas and dust like these. There are these 3 trunks of gas, and they're nicknamed the pillars of creation, and they're trillions of miles long. These are huge structures. The clouds look dense, but they're actually very sparse. These gas clouds are incredibly tenuous. You'd have to compress basically a mountain's volume worth of this stuff. Squeeze it down just to make a little tiny rock like this. To compress the gas and dust into dense stars and planets takes a supremely powerful event, one that can only follow the death of a giant star. In 2007, the Spitzer Space Telescope captured this image. A ball of hot gas behind the Eagle Nebula, evidence that a huge star has exploded and sent a vast wall of gas racing toward the pillars. There's a wave of hot material approaching the pillars of creation, and this may be a shock wave from a supernova, a dying star. Supernovas briefly outshine entire galaxies. Superheated plasma blasts into space at 70 million miles an hour. A mighty shock wave speeds toward the pillars of creation. When it hits, it will demolish them. It will also create new worlds. Supernova shock waves smash into the pillars, compressing the thin gas and dust into dense clumps. Each is a new star, a new solar system. A molecular cloud minding its own business gets blasted by a supernova explosion, crushing the cloud down into stars and planets. Wind back 4.5 billion years, and our solar system starts the same way. A supernova crushes a massive dusty cloud into a protoplanetary disk. A thin, nebulous cloud becomes a dense whirlpool of gas and dust, a solar system in the making. One star is destroyed. A new star is born, our sun and its planets. This is the first link in the long and unlikely chain of events that made our world. For Earth to even be here, we had to beat astronomical odds. A host of different factors have to line up to get a planet just like the Earth. You have to have the right distance, the right size, the right kind of moon. On Earth, all the conditions are just right for life. To get a world like ours, you need a lot of aces. Somehow, our solar system hit the jackpot. But the big question is, did it happen anywhere else? One of the universe's most violent events triggered the birth of our planet. A sparse cloud crushed into a dense swirl of dust. Some of this dust will become planet Earth. But how do tiny dust grains create entire worlds? A supernova explosion triggers a chain of events that will eventually create the Earth. The formation of our solar system. A hot ball of gas grows in the center. This will become our sun. The dust that swirls around it will form the planets. But first, the grains must stick together. So we have this interesting conundrum, right? This disk consists of gas and dust particles. They're about the size of, let's say, particles in smoke, right? Let's say cigarette smoke. So these are small things. And somehow, we have to get from those little grains to what we see on the Earth. Gravity is a powerful attractive force. It shapes galaxies and solar systems. But specks of dust are far too small to pull on each other. Somehow, they clump together to form planets. So if gravity doesn't bind them, what does? In Germany, scientists are on the case. They can simulate how dust behaves in space inside a huge tower. Here, we do freefall experiments. So the whole experimental setup, including our dust aggregates, are in perfect freefall. It is a simulation of space, but a very good one indeed. I think this is the closest you can get to space on Earth. Researchers place dust in a container and load it into a launch capsule. At the base of the tower, they lower it into a super powerful catapult. This launches the half-ton capsule from 0 to over 100 miles per hour in a quarter of a second. 400 feet up, the capsule reaches the top of the tower, then plunges back down. A drum of polystyrene balls 30 feet deep breaks its fall. All this gives just 10 seconds of zero gravity. Just enough time, they hope, for the dust to stick. 3, 2, 1, and go. Moments after the capsule launches, the dust inside becomes weightless. The grains clump together, just like the early solar system. These images reveal how dust particles came together 4.5 billion years ago to form the Earth. The force that binds the aggregates together is not gravity. They are too small for gravity to be efficient. We think the force that binds the aggregates together is electrostatic force. It's the same reason that, when you pull your clothes out of the dryer, you know how the clothes sometimes stick to you? Or That's the same effect that allows one dust particle to stick to another. Dust particles join to form balls of fluff. The little static charges that they have can make them stick when they hit. And you get something sort of like the dust bunnies that I have a lot of underneath my bed. These cosmic dust bunnies are planets in the making. They start out smaller than a pinhead, then grow. The dust is now in clumps, but it's still just balls of dust. Turning dust balls into rocks takes a whole new process, a cosmic electric storm. Space clouds build up charge, just like clouds here on Earth generating huge bolts of lightning. Balls of dust can turn into solid rocks by an energetic event like lightning. The electric bolts smash through the dust balls and heat them to 3,000 degrees Fahrenheit. In minutes, they cool and fuse into solid rock. Meteorites today still carry these ancient rock balls inside them. These tiny globules were once the building blocks of planets. To form the Earth, these tiny balls must collide, stick, and grow. Rocks begin to build up by accidental collisions, which can take a long time. Eventually, the protoplanets, as we call them, the baby planets, get the size of asteroids, kilometers across. The baby Earth is now the size of a few city blocks, big enough for a new force to take charge: gravity. At that point, a single asteroid will gravitationally attract a neighboring asteroid. And so those two asteroids that would have passed in the night are gravitationally attracted, and they hit each other. Once gravity starts to rear its head, things really speed up because instead of just randomly plowing through material and getting bigger that way, now it's starting to draw material in. Gravity pulls rocks together and holds them there to produce bigger and bigger piles of rubble. So this formation process, which was taking a long time to get to the size where gravity kicks in, suddenly gets kicked into overdrive and the planet grows very rapidly. But planets are more than just overgrown rock piles. These rocks are lumpy and inert. How did the Earth become round and full of life? The early solar system is a construction site for planets. Dust sticks together to form rocks. Rocks join to form asteroids. But most asteroids look nothing like Earth. And when you look at a close-up of an asteroid, it looks like some kind of distorted peanut, like a potato that's been sort of bashed. You can see giant craters and oblong shapes. The young Earth is one of billions of misshapen space boulders. To become a planet, it must first become round. That process only starts when it's several hundred miles across, when its own internal gravity begins to change its shape. Once you get enough material, enough mass, the gravitational force becomes stronger. Any giant mountain will be crushed down by the force of gravity. The gravity is so strong that it can actually break rocks, and the rocks themselves can act like a fluid, making an object round. Huge outcrops of rock crumble and fall. The immense self-gravity of the early Earth crushes it into the most efficient shape, a vast round ball of rock. A lopsided pile of rubble, transformed into a miniature world. The Earth has a new shape, but it's still just a ball of rock. Its structure will also soon change. Cosmic rocks and boulders still rain down from space. Each collision heats the ground. There's a huge amount of energy stored in an object that's moving rapidly. And when that hits the Earth, all that energy is dumped into the material. And that heats it up and melts it. And the Earth became molten and stayed that way for a long time. The young planet is no longer solid rock. It's a seething molten mass, just like this blast furnace at the Severstal plant in Detroit. Believe it or not, this process behind me makes life on Earth possible. They feed in ground-up iron ore, a mixture of rock and metal, just like the early Earth. Put iron ore in a furnace and the heat melts everything. This molten iron is at 2,700 degrees Fahrenheit. That's about the temperature of the surface of the Earth 4.5 billion years ago. Imagine an entire planet molten. In the distance, you would see thundering volcanoes spewing out lava. It would be a scene right out of Dante's Inferno. Iron is heavier than rock. Now molten, they separate. This is amazing. We're witnessing a process which created the very crust of the Earth billions of years ago. The crust that we walk on every day. Molten rock rises to the surface and cools to form the crust. Molten iron sinks underneath. Inside the Earth, it sank all the way to the planet's core. The rocky surface is where we live. But without Earth's molten iron core, none of us could survive. This process separated the iron from the rocky minerals. As the iron descended to the center of the Earth, it eventually created a magnetic field. And that's why we're here today. The molten iron swirls inside the Earth's core and generates a powerful magnetic field around the planet, a cosmic shield against deadly radiation from space. But the young Earth is still small, far smaller than the moon today. This newly formed world must grow. It must also avoid being blown to pieces. Thousands of protoplanets are hurtling around the solar system, and some are heading straight for Earth. It's 100,000 years since our solar system formed. The young Earth already looks like a planet. It's round. It has an iron core and a rocky surface. Yet, our baby planet is just a few hundred miles across. It has a long way to go. It must grow 4,000 times more massive. And it has competition. Thousands of other protoplanets shoot through the solar system, often colliding at over 20,000 miles per hour. You can find proof of this ancient destructive era in modern-day Arizona. Not meteor crater itself, that's just 50,000 years old, but the asteroid that gouged it out, that was 4.5 billion years old. Mark Sykes and Marvin Kilgore think the asteroid came from a violent event in the early solar system. The asteroid flew through space for billions of years. Then it hit Earth. They aim to find a fragment of the asteroid remnant from the period of planetary formation. About 6 miles from here is Meteor Crater. And that was an impact 50,000 years or so ago. And it spewed a bunch of pieces out. They're convinced the original asteroid was rich in iron, so they've come prepared with some impressive metal detectors. Does it work? Oh yeah, that's the sound we're listening for. But even with a quad-drawn metal detector, meteorites are hard to find. Yeah, are you pretty convinced there's nothing there? Yeah, I'm not detecting anything. They find metal, but no meteorites. My great discovery of the afternoon has been this bolt and this piece of wire. It takes hours of searching and many false alarms. Then, with the light fading, the detector sounds again. How about that? Success at last. This meteorite is over 90% iron and nickel. It could only form right in the core of a protoplanet. The protoplanet it came from must have smashed apart in a brutal collision. Well, in the early solar system, it was a pretty violent place. And these protoplanetary embryos would smash into each other, and they would shatter each other, exposing the interior cores like this. It was a very tumultuous time. Entire worlds, reduced to chunks of rock and metal and scattered into outer space. In the early solar system, these vast collisions are common. The young Earth is in danger. The period's name is the Titanomachy, literally, the War of the Titans. All rocky planets, the Earth included, go through this destructive phase. Sometimes they shatter completely. Sometimes one consumes the other. All the big guys are sort of competing with one another in a very violent way, actually, to see who comes out on top by eating all their neighbors. The battle lasts over 30 million years. Finally, thousands of protoplanets have combined into a few full-size planets. Mercury, Venus, Earth, Mars, and a fifth planet, Theia. It's racing toward Earth, our planet's last giant impact. Theia is the size of Mars, big enough to destroy the Earth. If that thing had hit us straight on, it could have literally blown the Earth to bits. And then we wouldn't even have a planet today. If this Mars-like object had a direct hit with the Earth, perhaps there would have been another asteroid belt where the Earth is today. But Earth is in luck. Instead of a head-on crash, Theia strikes a glancing blow. It's the most violent event the Earth has ever known. The impact turns the Earth back to a molten world, a vast magma ocean 600 miles deep. The Earth barely survives, and the encounter changes our world forever. Material blasts out into space see enough rock to build a mountain as wide as America, and 10,000 miles high. It would have been so much energy, so much catastrophe, huge amounts of material blasted off, and went into orbit around the Earth. The debris forms a huge ring around the Earth. This gathers together to form two rocky bodies, both orbiting the Earth. Something the size of Mars hit the Earth about 4 billion years ago. Lots of material would have been thrown off. We now think that it may have formed not only one moon, but two. For millions of years, two moons dominate the Earth's sky. Eventually, they drift together and collide. Two moons merge into one, the massive moon we see today. There's no other planet that we know of that has a moon as large as ours. In comparison to the size of the planet, we are almost a binary planet, two worlds going around each other. Without this large moon, we might not even be here. The moon plays a key role in the survival of life here on the Earth. And the reason is that the moon in its orbit stabilizes the Earth. The moon keeps the Earth spinning at the same angle. That steadies our climate. The fact that the Earth's axis stays in the same direction as it goes around the sun produces the seasons, but regular seasons, things that life can depend upon as it evolves. Earth is neither too hot nor too cold for life thanks to our distance from the sun and our massive moon. The Earth is not covered in ice or steam, but in liquid water. Yet that water must come from somewhere. The newly formed Earth is dry. To get water, our planet must once again face disaster. It's 500 million years since the sun first ignited. 4 billion years from now, the first humans will set foot on Earth. The moon has just formed, and the Earth is a desert. One of the more amazing ideas in astronomy is that the Earth started out hot and dry. There was no water here originally. As the planets formed, the sun's intense radiation vaporized the water in the inner solar system. Farther from the sun, temperatures were cooler. So, in the outer solar system, ice and water collected on comets and asteroids. While closer to the sun, the young Earth was dry. So things changed. What happened? How is it that now we have this wonderful water cycle? Well, the water probably came from somewhere else. If you want to have a solar system that has a lot of water in it, you have to bring it from the outer parts down into the inner parts. And you can do that through comets and asteroids. Comets and icy asteroids contain huge reserves of water. But they're hundreds of millions of miles from the young Earth. Then something changes. An event that tosses the asteroids and comets right across the solar system. Jupiter, Saturn, Neptune, Uranus take a cosmic roller coaster ride. So this isn't an event that happened when the solar system was young. Think of it as more of its teenage breakout years, where it just started to party for a while. The young planets have not yet settled into stable orbits. As their orbits shift, Jupiter and Saturn fall into an intricate dance. Every time Saturn orbits the Sun once, Jupiter orbits twice. So they always line up at the same spot. Each time, gravity tugs them in the same direction. First, they destabilize each other, and then the entire solar system. The whole thing just goes cooey. The analogy I like to use is, when a bowling ball hits pins, it just goes bam all over the place. That's what this would have looked like. Planetary pandemonium. Neptune and Uranus switch places. Saturn races outward. The giant planets scatter billions of asteroids and comets onto new paths. Many head for Earth. These asteroids and comets would have been scattered all over the place, right? Some of them hitting the Earth and Moon. Cosmic missiles bombard the Earth. We believe that every square inch of the Earth got hit by a comet or an asteroid during this period. It would not have been a fun time to be here. The bombardment lasts hundreds of millions of years, until finally, the gas planets settle into the stable orbits we see today, restoring order. But Earth itself has fundamentally changed. Those comets and asteroids were not just made of rock, but of ice, frozen water. Comets we know are made out of ice. They're dirty snowballs in outer space. And even asteroids can bring water and ice to the Earth. Our oceans are full, thanks to the cosmic hailstorm. So next time you're drinking a glass of water, realize that you're probably drinking comet and asteroid juice. The arrival of water is the final step to create a habitable planet. A sequence of catastrophes has created a world that's perfect for life. But has it happened elsewhere among the stars? Or are we alone? How did we get here? Planet Earth only exists because of a chain of extraordinary events. A lucky throw of cosmic dice. 5 billion years ago, the odds would have seemed extremely slim that a planet like Earth would form in a rather unremarkable arm in the Milky Way galaxy. It's like trying to throw 2 sixes but with dice that have thousands of sides. We know it happened once, else we wouldn't be here. But what are the odds it happened elsewhere? That other planets have life? Life like ours needs a planet with the right temperature and size. A stabilizing moon. A protective magnetic field. And just the right amount of water. The conditions must be perfect. Yet, amazingly, there may be countless Earth-like planets out there waiting to be found thanks to the sheer scale of the universe. We may find one any day now, with the Kepler Space Telescope. Jeff Marcy is mission co-investigator. It has only one goal, and that's to discover Earth-sized planets around other stars that you see in the night sky. Earth-sized planets are hard to spot. Before Kepler, astronomers took 20 years to discover around 500 planets. Most were gas giants, hundreds of times bigger than Earth. Since Kepler, that number has exploded. Kepler has already discovered a couple thousand planet candidates. Many of them are members of multi-planet systems. 2, 3, 4, 5, and even 6 planets all orbiting the same star. So we're finding an absolute avalanche of planets out there among the stars. Kepler has found one planet only twice the size of Earth and the right temperature for life. We don't know yet if this planet has other Earth-like attributes, like liquid water. But even if it doesn't, there are many more planets out there. Kepler has found only a tiny fraction of them because it only looks at a small part of the sky. It's not even looking at the whole sky. It's looking at a very tiny slice of stars in the galaxy. And in fact, if you were to look up, you could cover it with just your thumb. In the whole of our galaxy, there are 200 billion stars. Many will have planets. Based on our knowledge from Kepler and other searches, something like half of those stars, perhaps even more, harbor planets. That means at least 100 billion planets have formed in the Milky Way. Earth-like worlds may be rare, but it seems a safe bet they're out there somewhere. So the odds of getting an Earth-like planet are extremely small, much smaller than getting a double 6 at craps. But if you have a lot of dice, you're guaranteed to get 6s. And if you have a lot of planets, you're guaranteed to get Earths. There are so many planets in our galaxy. Even if the chances are 1 in a million, there should be thousands of Earth-like worlds. Our universe at large has hundreds of billions of galaxies, each of which is more or less like our Milky Way. So the number of planets in our universe is virtually uncountable. Alien Earths must be everywhere. Now, we haven't discovered even one of them yet, but statistically speaking, it is a rock-solid certainty. There are millions of billions of planets like the Earth out there. And with that many Earth-like planets, surely some of them will have intelligent life. I would bet everything. I would bet my house that there is another Earth out there somewhere. There really can be no doubt that elsewhere in our universe there are other smart critters who are asking themselves, gee, I wonder if there are any other intelligent species out there in the universe. Throughout history, the heavens inspired awe and wonder in human observers. Our ancestors watched the skies with amazement, imagining the power of the bright objects that we now call planets. The fact is that for as long as there have been people, we've looked at the sky. We've looked at what we see there. We've asked the question, What's the connection between that and us? The ancients erected standing stones, temples, and pyramids, from which to predict cosmic events and to worship the gods in the sky. But the first telescopes revealed a universe unlike anything we could have imagined. We began to see what was really out there. Not gods, but planets, stars, immense clouds of gas. In 1755, Immanuel Kant, German scientist and philosopher, turned his attention to these huge clouds, or nebulae, and in the process came up with one of the first modern theories of how the solar system formed. All of these beautiful clouds in interstellar space have turned out to be very important. It's where stars are born. It's where planets form. Kant's key idea was that nebulae could collapse in and condense into planets and stars. It's known as the nebular theory. 250 years later, Kant's theories still help to explain the birth of our solar system. Today, new observations are revealing how the sun, planets, and moons of our solar system took shape. Scientists like Professor Jeff Hester are solving many of the long-standing mysteries of the formation process. We now have answers to questions that people have asked themselves for, as long as there have been people. And it changes the way that we think about ourselves. Dr. Michelle Thaler is an astronomer working with NASA's Spitzer Space Telescope. It's the fourth and last satellite of NASA's Great Observatory program, and it gives scientists a totally new view of the universe. What's happening now in astronomy is we're finally seeing the universe as it really is, not just as humans perceive it. One way to establish how our solar system forms is to watch other distant systems take shape. But if Kant was right, and new solar systems form deep within clouds of interstellar gas, we might never see this happening. Our own senses, what the human eye can see, turns out not to be the whole story. There's so much more out there that the humans just don't have the capability to see. Naturally, objects emit infrared radiation. Infrared has a longer wavelength than visible light, so it's not scattered by dust. Conventional telescopes that use visible light cannot see inside a dusty nebula, but infrared sensors on board Spitzer can. The same principle is used by firefighters. This room is completely full of smoke. There is no way that you can see with your eyes, or with a regular camera, what's going on inside. So fire departments use infrared cameras to be able to see people inside a smoke-filled room and actually see the heat of a person's body. This is exactly how Spitzer works. Spitzer actually looks through these giant clouds of smoke and dust to see planets inside. Just like these guys can find the people. Visible light is completely blocked by things like smoke and dust, but infrared light is a longer wavelength. Actually, it's just sort of a happy coincidence for us that nothing stops it in the chemistry of smoke and dust. I think you really get a sense now that we're able to see where we've never seen before using the Spitzer Space Telescope. A camera in a smoke-filled room is one thing. A telescope in outer space is quite another. On the ground in 2003, Thaler and her colleagues wait anxiously for Spitzer's first data. At stake is a unique view of the origins of our own solar system. Literally, no one had ever seen what the universe looks like in that type of light. So at first, we were amazed at the beauty. I did not expect Spitzer's images to be as compelling visually to me as they turned out to be. They are beautiful, but these are not just pretty images. Crucially, by observing distant worlds as they form, we also learn more about the birth of our own system. One of the privileges of observing star and planet formation is that you're effectively looking back in time. You're looking at what we must have gone through billions of years ago. What this glimpse back in time reveals is a snapshot of the earliest stages of solar system formation. This is our best ever view inside a nebulous collapse. We've actually been able to observe with Spitzer the moment where the dust begins to collect together and then get warm, and then finally, young stars emerge. So it turns out Kant's 250-year-old theory is essentially correct. Our own nebula began its collapse 4.6 billion years ago. It's likely that the nebula had been slowly spinning in space ever since its formation. But as its material collapsed, it began to spin much faster. This is down to the law of physics known as conservation of angular momentum. As the nebula contracts, the same amount of energy is now concentrated in a smaller space. To keep the same momentum, rotation speed must increase. As our nebula began to collapse under its own gravity and spin faster, a dense clump of matter formed in the center. It's called a protostar. At first, its heat was due to friction. But when the clump reached 18 million degrees Fahrenheit, nuclear fusion kicked in. 4.5 billion years ago, our star was born. Hydrogen atoms fused together to form helium, and in the process released photons. It's the first light made by our sun, and it will keep on shining for 4 billion years. A vast nuclear furnace nearly 1 million miles across. From a distance, this process seems almost peaceful, with the sun's power gently radiating out into the early solar system. There was all sorts of activity going on. Things were changing rapidly: violence, explosions, intense radiation. We had a pretty spectacular origin. I think recent research suggests the solar system's birth was far from peaceful. Our sun may in fact have been born out of one of the most violent events in the cosmos, the explosive death of another star. And even before that, it seems there was an explosion so huge that created an entire universe, the Big Bang. No one knows what caused it, but we think that the Bang created space, time, and all the matter in the universe. Yet for astrophysicists such as Professor Stan Woosley, there's a puzzle. The Big Bang produced almost none of the 88 naturally occurring chemical elements. When we look around, we don't just see hydrogen and helium. We see planets and people. And we're made out of carbon and oxygen. And planets are made out of iron and silicon. And that didn't all come from the Big Bang. It had to come from somewhere else. Here on Earth, we have learned how to create new elements for ourselves, nuclear technology. The same thing happens inside stars. Hydrogen and helium from the Big Bang fuse to form heavier elements. And if the star is big enough, at the end of its life, it does something spectacular. It explodes. The energy of a supernova explosion is essentially equal to all of the energy that the sun will put out in its 10 billion year lifetime. And yet the supernova delivers this in less than a day, and then expands for a few months afterwards. As it expands, it's as bright as an entire galaxy. It's as bright as 1 billion suns. Extreme nuclear processes within the dying star fuse the elements the star created in life to make heavier elements. As the star explodes, it blasts these into space. In its death, it creates the essential elements for making planets and life elsewhere. It spews the products of millions of years of nuclear reactions out into the gas in between the stars. This is the basis for some of the clouds that eventually form new stars. Yet they are spread so thin that it's difficult to know what triggers a cloud like this to collapse. The best way to find out is to examine the material that once made up the cloud. And that means examining the two oldest types of material in the solar system, asteroids and comets. But first, scientists need to bring back a sample from outer space. Comets are relics from the earliest days of the solar system and may hold clues to our origins. But before scientists could study them in depth, they needed samples. In 1981, this man, NASA's Dr. Peter Tso, started to work on his idea to return comet fragments to Earth. It's almost like a space forensics. It's like you see some television program or crime scene. They find a piece of paint chip or hair or something very similar to what we're trying to do. Tso and his colleagues designed the Stardust probe to travel over 300 million miles from Earth and collect dust grains from the comet Wild 2. There's just one problem. The dust particles will be moving up to 6 times faster than the speed of a bullet. Yet, it's vital so gets them back to Earth undamaged. So, what I need is special material to be able to contain the high-speed bullet. I need to capture it without breaking up. I need to capture the bullet without breaking the bullet. It takes Sue over 2,000 experiments to refine his comet-catching material. It's made of the same chemical as glass, silicon dioxide only, 1,000 times less dense. Sue calls it smooth gradient silica aerogel. If anything can stop comet grains, it's this stuff. With aerogel capture cells on board, the probe is good to launch. On February 7, 1999, it blasts off atop a Delta rocket. We have main engine start and liftoff of the Stardust spacecraft, returning a time capsule with the elements of the formation of our solar system. Its 2 billion-mile journey takes nearly 5 years. But eventually, the night of the comet encounter arrives. At mission control, all Sue and his colleagues can do is wait. We had done many simulations, but still questions. Will it run into a comet? Even if it doesn't run into a comet, did it collect dust at all? It would be horrible if it comes back in no dust. Finally, in 2006, the capsule re-enters Earth's atmosphere. It makes a safe landing, and scientists rush its precious cargo to the lab. As soon as they open it, they know the mission is a success. If I capture one particle that I can see with a naked eye with a microscope, I will be pleased. But I caught more than 36 of them. It's an incredible achievement. These are the first pristine comet particles ever to arrive on Earth. The grains may be tiny, but they contain a wealth of information. It will take many years really to understand the formation of the solar system. It will take probably a couple of decades to milk all we can from the Stardust samples. The team may have to wait decades for all the results. But in the meantime, others are trying a different approach. Comets aren't the only source of material from the early solar system. Meteorites are ancient too, and they have one huge advantage: they come to us. The amazing thing is that anytime you pick up a meteorite, with a very few exceptions, you take it into the laboratory, you date it. The answer is, it's 4.5 billion years old. 4.5 billion years old. These are pieces of the early solar system. And so here you have in your hand a piece of something very substantial. That connects you, and connects our existence, and connects the history that brought us to be with this larger universe. After extensive analysis, Esther's team discovers unstable isotopes of iron-60, locked inside the meteorites. It's totally unexpected. Iron-60 decays relatively fast, so it must have come from close by. If it came from any great distance, it would have had time to decay into a different isotope before the meteorite could trap it. Only a supernova can make iron-60. So there must have been an active supernova close to the infant sun. To come along with a piece of hard evidence that says, nope, early sun, early solar system were in a violent environment near a massive star, experienced a nearby supernova. It was surprising. We realized that this is going to change the way that people think about what goes on. This is going to change our understanding of the origins of the solar system. Despite the violent forces being unleashed, our solar system may have formed right alongside a supernova. These are exquisitely violent events, and they reshape everything around them. Shockwaves from exploding supernovae pummel everything within 20 light-years. A galactic bomb blast. What's astonishing is that all that destructive force may have been exactly what was needed. Blast waves can push dispersed matter together, like a broom sweeping up dust. So, the collapse of our giant cloud of dust may have been triggered by the blast from the nearby supernova. They'll send shockwaves and compress the gas for light-years around them. And that compression triggers the birth of other stars. The blast wave could have swept together the material of our nebula. When compressed enough, gravity would start to have an effect, and the cloud would begin to collapse. Within the cloud swirling about the infant sun, the planets are beginning to take shape. And today, scientists are beginning to understand the astonishing processes that form them. For years, The process of planetary formation has puzzled scientists. Some astronomers now believe planets grow within the disk of gas particles surrounding a newborn sun. But this material is spread too thin for gravity to pull it into clumps. Then, in 2003, some informal experiments on board the International Space Station shed some light on this long-standing mystery. Astronaut Don Pettit spends his free time in space, messing around with a few experiments to see how particles behave in zero gravity. He takes different grains such as coffee, sugar, and salt, places them in pouches, and watches as they begin to attach to each other. He realizes that the friction between them, as they rub together inside the pouches, is creating an electrostatic charge that pulls particles together and forms them into clumps. The same electrostatic charges would have been created if the experiment were carried out on Earth. But on Earth, the far stronger force of gravity would have made it impossible to observe the same results. Pettit and his colleagues realized that what they are seeing in the zero-gravity conditions of the space station would also have occurred in the zero-gravity environment of the early solar system. The particles in the protoplanetary disk may somehow get charged and attract each other. It's a process known to planetary scientists such as Jacques Lassalle as accretion. We see signs of accretion in our daily lives. Raindrops condense as very, very tiny droplets around small little pieces of dust. And they collide with one another as they fall in much the same way that grains collide in the solar nebula and accrete into bigger objects. Once the clumps reach the size of mountains, they exert a significant gravitational force. It's more powerful than the electrostatic force. So the whole process accelerates fast. In about 1 million years, the clumps can grow into larger planet disks or pieces of planets, and can keep on growing into full-size planets. Gravity keeps these planets locked into their orbits around the sun, traditionally understood as a mysterious pulling force. Since Einstein, scientists have a new understanding of gravity. Most people know that it's the sun's gravity that keeps planets moving in orbits around the sun. What we're going to do here is we're going to take a little bit deeper look at what the nature of gravity really is. Now, Newton's first law of motion, law of inertia, says that an object moving in a straight line at a constant speed will keep doing so. So here, in the overhead view, we're looking down at a flat surface. And if I take this ball, which represents a planet, and I roll it across the surface, sure enough, it moves in a straight line at a constant speed. Now, Einstein said there's actually more to it than that. Einstein said that if you took a mass, for example, the mass of the sun, represented here by this plunger, that mass had the effect of distorting the shape of space-time. Now, to us, it doesn't look distorted. If you look on the overhead shot, it still looks as flat as it did before, just like a chessboard. But in fact, it is distorted. And so now, when I take my planet and I move it through this distorted space-time, it tries to follow a straight line, but there's no straight line available for it to follow. And so instead, what it winds up doing is it winds up moving around the central object on an orbit. It's that effect of that curved space-time that we usually call gravity. Gravity exerts an equal force in every direction. So its effect is always to attract matter evenly toward the center of a body. Therefore, when it's strong enough, gravity will resculpt any body into a sphere. This is why all planets in the solar system form nearly perfect spheres. With a diameter of over 300 meters, no other shape is possible. All the planets are roughly spherical and all come from the same original disk. But they end up as radically different worlds, from rocky Mars to gassy Jupiter. The differences are primarily down to one basic law of physics. Different kinds of material condense at different temperatures. It has to do with, given a given temperature, what is a gas and what is a solid, and that's it. At first, all the matter around our young star is so hot it's in a gaseous form. Then, further out, as things cool, material begins to condense out of the cloud-like snowflakes forming on Earth. In the inner solar system, closest to the sun, it stays hot. Way too hot for gases or ices to condense. At these temperatures, they'd evaporate instantly. But metallic particles can condense here. And the planet that forms in this zone is highly metallic, Mercury. Astrophysicist Steve Desch is an authority on planetary formation. His research has shown him just how hostile a world Mercury must be. It has no atmosphere. It has no oceans. It's just rock. And the part that faces the sun tends to get hot enough to melt lead, for example. It's many hundreds of degrees Fahrenheit. The fierce heat is due to Mercury's proximity to the sun. It's almost 3 times closer than the Earth. Move further out and the temperature eases a little, by around 1,000 degrees Fahrenheit. Now, more rocky particles can condense. So, the rockier terrestrial planets, Venus, Earth, and Mars, form in this region. Since Venus orbits around 30 million miles further from the Sun than Mercury, we could expect it to be a more hospitable place. Venus is probably the closest thing we have in the solar system to your conception of hell. The pressures are immense. The temperatures are high. And it rains sulfuric acid. Around 26 million miles further, our home planet. The Earth has been nicknamed the Goldilocks planet. It's not too hot, and it's not too cold. It's orbiting at just the right distance from the Sun, and that makes it very conducive to life. Earth has a protective ozone layer to shield us from harmful UV radiation, and a magnetic field that deflects lethal cosmic radiation. Earth is also the only inner planet to have a large moon. Today, scientists like Gary Loughran still study the lunar samples first brought back by the Apollo astronauts over 30 years ago. Loughran works in the Secure Lunar Storage Facility, where NASA keeps most of the 842 pounds of rock brought back from the moon. For years now, scientists have been studying the samples to discover how the moon and the wider solar system may have formed. It's an invaluable resource for geologists, and the Apollo astronauts made it a top priority to bring samples back, even if it meant ignoring orders. Neil Armstrong personally made sure that we got a bunch of rocks, by basically sort of disobeying the rules, as I understand it. And he kind of snuck out of the view of the TV camera, which he wasn't supposed to do, and filled up a box full of rocks. When the samples are analyzed back in the lab, they soon give up some surprising information. We found out quickly that the chemistry was very different from the Earth, and it wasn't the kind of chemistry we expected from our previous ideas about the formation of the moon. The lunar rocks, and therefore the moon itself, turn out to be younger than was previously thought. All the theories we thought of before we went there kind of went out the window really quick. And it took a few years before good ideas began to come forth. According to nebular theory, there should not be enough of the right material left over from planetary formation for moons to form in the inner solar system. It remained a scientific conundrum until, after decades of painstaking work, scientists came up with a new theory. A violent and devastating scenario that involved the Earth experiencing a head-on interplanetary smash. 1969. Neil Armstrong was the first man to walk on the moon. Only when the Apollo astronauts brought back lunar samples were scientists finally able to understand how our moon may have formed. Their study of chemical isotopes in the samples suggests the moon contains material that was once part of the Earth. It was a totally unexpected find. Scientists were at a loss to explain how this material got there. But eventually, a bold new theory emerges. A theory suggesting that in the early solar system, there were not 8, but around 20 planet-sized objects orbiting the Sun. When you think about the early stages of planet formation, you can think of it as a sort of pinball game, where there are these objects that are careening all over the place, occasionally running into one another. 4.53 billion years ago, the young Earth is on a direct collision course with an object named Theia, a body the size of Mars. If we had that collision today, it would probably be the end of mankind. It would be the equivalent of many, many hydrogen bombs exploding on the surface of the Earth. It's a world-shattering impact, blasting material with such force that billions of tons of rock escape Earth's gravity and eject into space. This material is captured by the Earth's gravitational pull and enters into orbit. Over a few million years, it amalgamates and becomes our moon. The collision is further evidence of a violent early solar system, the period when countless bodies followed chaotic orbits. Often they'd wreak havoc, but some objects became permanent features of our system. The two Martian satellites, for example, Phobos and Deimos, are both believed to be former asteroids captured by the gravity of Mars. These two moons are relatively tiny. Even the larger body, Phobos, is just 1/10 the size of our moon. Although Mars itself is only 1/3 the size of Earth, it has some of the most extraordinary features in the solar system. Mars is a spectacular planet, a geologist's wonderland. For example, it has the solar system's largest canyon, Valles Marineris, which has side tributaries that would dwarf the Grand Canyon on Earth. It's about the length of the United States. It has the solar system's largest volcano, Olympus Mons, which would dwarf Everest. Mars is the last of the 4 inner terrestrial planets, the rocky bodies orbiting inside the asteroid belt. Have these planets stopped growing at their present-day size? Was largely down to the question of supply. Rock and metal were scarce in the early solar system, making up only around 0.6% of the total material available. Also, the inner planets couldn't accumulate gas compounds because it was too hot for them to condense here. All of the gas compounds condense much further out. Before we reach this zone and the outer planets, there's the asteroid belt to contend with. Science fiction paints this as a crowded zone, difficult to cross. We now know that there are at least tens of thousands of asteroids in the asteroid belt that are a mile or larger in size. Nevertheless, it would be very unlikely, if you were piloting your spaceship through the asteroid belt, to run into one of these. In fact, we have to aim very carefully to get space probes to visit asteroids. The average distance between asteroids in the asteroid belt is about 1 million miles. As we traverse the asteroid belt, we hit an invisible but critical border. It's called the frost line. Cross this boundary in space, around 280 million miles, out from the Sun, and we find totally different kinds of planets. There was a frost line somewhere in the asteroid belt, beyond which it was cold enough for water to condense. And this was a gradual transition, but a very important one. Beyond the frost line, the outer planets take shape. These are very different worlds to the inner planets, and that's due to the kinds of substance that can condense in this cooler region. Colder than -100 degrees Fahrenheit, hydrogen compounds like water, methane, and ammonia are able to condense. And there are trillions of tons of this material available in the early solar system. But it's only once the outer planets reach 10 times the mass of Earth that their growth really takes off. At that critical mass, they have enough gravitational influence to start sucking up trillions of tons of gas. There's a snowball effect. As they get bigger, the planets attract ever more gas. It was a race about how fast these cores could grow compared to how long the gas disks hung around. Jupiter and Saturn just happened to be at the right place in the solar system. They fast become gigantic superplanets. And since gas now makes up 90% of their mass, they are also known as the gas giants. Largest by far is Jupiter. This giant planet has a mass over 300 times that of Earth, while its volume is more than 1,000 times greater. According to Hal Levison, we're fortunate that Jupiter did reach this size. The planet's gravity is so powerful, it often changes the trajectory of comets that could otherwise enter the inner solar system. Jupiter actually plays the role of a protective big brother that protects us from the hostile environment that exists beyond its orbit. And in particular, there are a lot of these small icy comets that could come in and hit us. That Jupiter deflects away, throwing them out of the solar system. Saturn is the second largest planet in the solar system. Whenever I show people planets in my telescope, I always save Saturn for last. It's beautiful. It's so stunning. It's definitely a gorgeous planet because of its large rings. The rings are made up of billions of fragments. These fragments continually grow and disintegrate due to the conflicting gravitational forces of Saturn and its moons. Uranus lies nearly twice as far out from the Sun as Saturn. Both it and Neptune are icy worlds with much less gas than the other gas giants. In a sense, they got to the feast too late. Uranus is a plain-looking place, a flat blue-green color, thanks to a layer of methane high in its atmosphere. Since it forms further out, it becomes an ice giant rather than a gas giant. Temperatures average minus 350 degrees F. Since Pluto has been officially downgraded to dwarf planet status, Blue Neptune is now our outermost planet. Until recently, these bodies were thought to mark the very edge of our solar system. Our idea of the solar system changed drastically in 1992, when this structure that we call the Kuiper Belt today was discovered. Around 28 billion miles out from the Sun, the Kuiper Belt is home to an estimated 70,000 large icy objects. There is a whole population of leftover dregs of planet formation. You can think of it as a place where these things haven't quite come together. When we look back in at our own solar system, it becomes clear there are problems with the standard theory of how our planets formed. It's interesting. When we try to apply our models, our understanding of planet formation, to Uranus and Neptune, they fail utterly. You just can't build those planets where we see them today. There simply should not have been enough material available at this distance from the Sun for planets this size to grow. It's a mystery. Uranus and Neptune seem to be in the wrong place. And this is just one of several mysteries that standard nebular theory cannot explain. There's also the enigma of the Kuiper Belt. According to the model, it shouldn't really be there. Even more puzzling, our moon's craters all seem to date from the same time. Together, these problems threaten to undermine scientific understanding of how the solar system formed. The moon may be our closest neighbor, but it still harbors secrets. With no substantial atmosphere or weather, the lunar landscape experiences little change. So, it was believed that one impact strike every few thousand years would be enough to explain its cratered surface. But then, the Apollo missions brought back lunar rock samples, including crater debris thrown out by ancient impacts. And these samples tell a very different story. It became clear as we studied the moon that a large number of the impact craters formed around 3.9 billion years ago. And clearly, there was a high concentration of impacts on the moon during that time. Lunar geologists use radiometric dating to assess the age of the samples. It came as a big surprise to find that a high proportion of moon craters formed during one relatively brief period of bombardment. Dr. David Kring is an expert on this phase, known as the late heavy bombardment, or lunar cataclysm. This evidence from the moon is actually telling us something about the entire origin and architecture of the solar system and how it evolved. Tens of thousands of large meteorites must have hit the moon during the lunar cataclysm. Earth, too, must have taken a pounding. Today, only younger craters, like this 20,000 to 50,000-year-old example in Arizona, remain on Earth. Most older craters have disappeared. But 3 to 4 billion years back, there'd be no chance of missing them. We're talking about 20,000 to 40,000 impact craters that would have had enough energy to change global conditions. Where could such a vast number of impact objects come from? Within the impact craters, we have chemical traces of the objects that produce them, and those point to the asteroid belt. It seems to match. The objects that once hit the moon are chemically consistent with the rocks found in the asteroid belt. So this is almost certainly where they came from. But today, most asteroids are in stable orbits. There's nothing obvious that could force thousands of them out of the asteroid belt and into the inner solar system. So for decades, the bombardment was a scientific puzzle. In 2004, Hal Levison had a eureka moment. Working with an international team, he came up with a new model of solar system formation. It's like a light going off. You sit in your office and you say, "I've solved this problem. This problem people have been working on for decades. And I'm the only one in human history that understands this little part of the problem we're trying to solve. Levinson's idea assumes that the planets might have formed in very different orbits, and then moved. Most scientists had believed the solar system stable and relatively predictable. But many experts now think this is wrong. This flies in the face of conventional wisdom. Astronomers probably always thought the planets formed where we find them today. These new numerical simulations, which show that they migrated a substantial amount and even had close encounters that caused them to switch their order, are startling and new. In Levinson simulations, Jupiter and Saturn tugged on each other whenever their orbits came closest together. But overall, these pulls canceled out. Only when Jupiter circled the Sun exactly twice for every time Saturn circled once did something dramatic seem to occur. It's called a 2-1 resonance, and it happened 3.9 billion years ago. And that configuration actually makes the planets jiggle with one another. They perturb one another. Instead of canceling out, the two planets' gravitational tugs then work in the same direction. To Levinson, it's just like pushing a swing. Each well-timed push nudges the swing higher. For Jupiter and Saturn, each gravitational nudge stretched their orbits until they reached their present-day patterns. But the process had a fateful impact on other planets. Uranus and Neptune can't stand that at all, and they just go totally bonkers. The orbits cross one another. They gravitationally get close to one another. One of them gets thrown out, the other one gets thrown in. They rattle around off Jupiter and Saturn. According to the theory, Uranus and Neptune may even switch places, ripping surrounding swarms of asteroids out of their orbits. It's a recipe for disaster. Some asteroids are thrown out into space, while others are pushed into the Sun. Thousands slam into the inner planets and Earth's moon. It sounds like an improbably chaotic transformation, but the evidence now suggests this did happen. It could never happen today. Jupiter and Saturn are now too far apart. But this event may have been a key moment in the formation of our solar system. But the really incredible thing is that it could so easily have turned out very, very different. You could have had the wrong type of star. You could have had too many giant planets. There are many ways things can go wrong. And we're right there on that thin, lucky line of existence. Instead of the diverse solar system we now see, we could have remained forever as ashes, gas, and dust. And what of our future? 5 billion years from now, as our sun runs out of fuel, it will expand, consuming some of the inner planets. Other planets may survive as ghost worlds, still orbiting their dead sun. There will be no life of any kind. But for now, we are lucky to be alive. The Earth from space, a unique perspective. It helps us understand the forces that continue to shape our world. Earth has 7 continents. This is the story of one of them. North America takes up 16% of our planet's total landmass, more than Europe and the Middle East combined. It is home to Yellowstone National Park, the Grand Canyon, Mount St. Helens, and the largest group of freshwater lakes on the planet, the Great Lakes. It's also home to the world's oldest rocks that have helped to reveal our planet's dramatic history and unravel the secrets of the birth of America. The cool thing about this planet is that, with the eyeballs of somebody who's thinking about rocks, you can look at a layer of rock and say, hey, that's not a layer of rock, that's an ancient swamp. Or, that's an ancient sand dune. To decipher North America's past, geologists must first find its origin. In Canada's Northwest Territories, some 200 meters from the nearest city, this rock outcrop near the Acasta River is the first chapter in the story of the birth of a continent. Dr. Wouter. Bleecker is working here to pinpoint just how old America really is. Here at Acasta, we'll find the oldest continental crust, actual rocks you can stand on. So, we basically see the initiation of continental growth here. This is where it starts. The birth of America is set in motion 4.6 billion years ago. As our sun explodes into life, gas and debris hurtle around it and eventually, 8 planets emerge from the vortex. At more than 12,000 degrees Fahrenheit, one of these newly formed planets appears nothing more than a ball of boiling lava. Earth is a primeval hell. The heaviest elements, like nickel and iron, sink down toward the center of the Earth and form its core. The lighter elements, including oxygen and silicon, rise toward the surface and form oceans of molten rock. Slowly, the Earth's surface cools. The lava solidifies and forms patches of crust. As this crust grows, it gets heavy and sinks back down into the mantle. Deep below the surface, it remelts, and the lighter elements rise up again, eventually forming granitic lava. Granite is less dense than other rocks in the mantle. It floats on the surface. As it solidifies, it forms rafts of land. Think of it as the scum on a pot of soup. If you boil that soup long enough, that scum will nicely separate and float on top of the soup. And that is what continental crust is. It's basically the scum of the Earth. Here at Acasta, this scum is actually a granitic rock called tonalite. Tonalites are important because they are the first materials that actually make stable continental crust. All continents contain chunks of tonalites that date back over 500 million years. These form rafts of continental crust called cratons. North America is made up of at least 6 of them. For researchers to date the birth of North America, they must find the earliest. And to do that, they have to date tonalite from all over the continent. It's a complex process. They look for microscopic evidence created as the rock was formed, telltale mineral crystals tough enough to survive over eons. One of the toughest minerals of them all is zircon. Zircon contains uranium-238, an unstable radioactive isotope. Scientists know that this isotope decays, gradually turning into lead. Importantly, they also know exactly how long this process takes. Imagine that the top half of this hourglass is uranium-238, and the bottom is lead. Over 4.46 billion years, half of the sand representing uranium will drop into the compartment representing lead. That's uranium-238's rate of decay, its half-life. By measuring the amount of lead and uranium isotopes in the zircons from the Acasta tonalite, scientists can pinpoint the rock's age and figure out how old this part of North America is. The tonalite found near the Acasta River in Canada's Northwest Territory is 4.03 billion years old. This is the oldest rock in the North American continent at this point in time, right here at Acasta, within the core of the Slave Craton. These tonalites predate most other rocks by billions of years. They are the oldest rocks ever discovered. The core of the Slave Craton in North America contains the oldest surviving landmass on Earth. The next challenge is to figure out what embryonic North America might have looked like. Professor Ron Blakey is an expert in continental mapping at the University of Northern Arizona. When the early continents formed some 4 billion years ago, they were probably scattered about the surface of the Earth. But this far back, we would just be completely speculating on what the position of the continents would be. This is our planet today. 7 distinct continents, all surrounded by water. But take away the oceans, and we see that a hard outer shell, or crust, covers the Earth's surface. The oldest and thickest crusts form our continents. That's around 40% of Earth's skin. The rest is underwater, oceanic crust. Oceanic crust forms a thin layer at the top of the Earth's mantle, and a 1,800-meter thick layer of superheated molten rock, magma. Heat escaping from the center of the Earth creates convection currents in the mantle. It's believed that this slow boiling motion breaks the crust up into pieces called tectonic plates. In some places, magma from the mantle escapes through the gaps between plates. As it rises and solidifies, it forms new oceanic crust and forces the plates apart. In other places, the mantle drags oceanic crust down, consuming it. As a result, the Earth's crust is constantly moving, traveling about 30 meters every million years. Ohio University professor Damian Nance specializes in plate tectonics. We create, if you like, a conveyor belt. And continents are carried by these conveyor belts, much like suitcases on an airport conveyor belt. Starting some 4 billion years ago, Earth's churning interior and the cooling of its surface create and move these rafts of land. They collide and form continents. Some of these merge, forming supercontinents: Valbora, Rodinia, Laurussia, and Gondwana. 3.5 billion years after the oldest surviving continental crust forms, Gondwana moves slowly north from the South Pole, breaking up into smaller pieces. Eventually, these pieces recombine with others, forming a landmass of incredible size. From this, North America will eventually emerge. Over billions of years, the dynamic movement of Earth's crust has shaped and moved entire continents. When these landmasses collide, they produce mountains. These are the Appalachians, the oldest surviving mountain range on the continent. Today, they stretch nearly 2,000 miles southwest from Newfoundland to central Alabama. But when they first appeared, over 270 million years ago, North America still did not exist. These mountains crowned a supercontinent called Pangaea. When they were at their maximum height, they would have been perhaps the most profound mountain range existing on the planet. In a road cut in the Appalachian foothills, Ohio University professor of geological sciences Damian Nance examines the geology exposed in the Appalachians today. What may look like a rather unimpressive wall of rock to the casual eye has proven to be a geological Rosetta Stone in this part of the Appalachians. It records the very first collisional event in the building of the Appalachians. These belts of folded rocks are the surviving record of 3 titanic collisions that created the mountains. Billions of years after the creation of the Acasta tonalite, 2 ancient continents begin to collide. As these 2 continents close in on each other, the ocean floor is pushed down underneath what will become Africa. Gradually, the ocean is consumed. Huge sections of the seafloor are dumped on the edge of the continent, creating ridges and valleys. As the continents continue their inexorable journey, island land masses are compressed between the 2. The debris accumulates, now on dry land. The continental collision forces the debris further upward, driving the Appalachian Mountains higher. It's the geological equivalent of a car crash. If you imagine a wreck between a truck and a much smaller car, the first thing that happens when the 2 hit each other is a collision between the front of the 2 vehicles. You can think of that as the first collisional episode in the Appalachians. The next thing that happens is the truck hits the windshield. And that, if you like, is the second collisional event in the Appalachians. And finally, the car disappears under the truck, and that is the climactic collision. The one that produced the final elevation and brought the whole process to a close. This mountain-building process involves hundreds of thousands of cubic miles of rock. It's thought the Appalachians originally rose higher than the present-day Himalayas. Today, they are a shadow of their former selves, cut down to size by another powerful geological process: erosion. One of the great lessons of geology is that mountains are ephemeral. They go up, and they go away. They're pushed up by forces inside the earth, and they're eroded away by erosion. And erosion can happen pretty fast. I mean, if you merely erode 1 millimeter a year, 1,000,000 years is enough time to get rid of a kilometer of mountain. The mighty Appalachians were tamed by another powerful enemy: water. When water freezes, it expands in volume by as much as 8%. Here, a bottle of water rapidly freezes. The ice expands and the bottle cracks. This same action applies to rocks. Water freezing in cracks breaks them apart. When temperatures rise, the ice melts and washes away the debris. Wind and rain add to the process. And over eons, they have the power to utterly transform the landscape. Erosion can do incredible damage to a mountain range. And we can see that in the modern Appalachians. The modern Appalachians are simply the remnants of this once vast and very high mountain range. Today, Pangaea's eroded mountains are in North America. How they came to be here is the next step in the story of the continent. Continents trap heat. Continents act a little bit like a book on an electric blanket. If you put a book on an electric blanket, it gets hot. The book acts as an insulator, trapping heat underneath it. Continents do the same thing with heat generated in the Earth's interior. So, if you put a very large continental mass together, like Pangaea, heat builds up beneath it. Pangaea is big. It's nearly as big as all of our 7 continents put together. The temperature builds up underneath the continent and heats it up. As the rock absorbs heat, it arches. Then, at its weakest points, it cracks, including along the line of the Appalachian Range. It's a process called rifting. Here's North America about 210 million years ago. If we look carefully, we can see some of the rifting between Africa and North America, where the Atlantic Ocean will eventually form. Just for reference, New York is right here. So, the distance from New York to West Africa wasn't even as great as the distance from New York to Chicago. As Pangaea cracks, it creates long, thin valleys. These elongated depressions fill with sediment washed down from surrounding highlands. Today, we call one of these the Newark Basin of Pennsylvania, New York, and New Jersey. This sediment, now solidified, has been quarried. Today, you can see it on the streets of New York City every time you look at a brownstone. 230 million years ago, the rifting between North America and Africa creates a new ocean, the Atlantic. As the two land masses continue to pull apart, water floods the widening gap. The continental landmass we call North America is created. Nearly 4 billion years after the first land formed, its shape and features look different from the continent we know today. Other geological processes will change them. America is constructed by plate movement, but it is shaped by fire, ice, and water. 150 million years ago, Pangaea's disintegration begins a new phase in North America's evolution. Some of the continent we recognize today is submerged underwater. Millions of years after Pangaea splits, a shallow sea stretches across the interior of the North American continent. It's called the Western Interior Seaway. It bisects North America from the Arctic Ocean to the Gulf of Mexico. It is the hunting ground of mighty carnivorous reptiles, mosasaurs, and plesiosaurs. And you think, wow, that's amazing. A sea was on this continent. But it's not that amazing. A continent like North America is quite large, yet the highest point in North America is Mount McKinley, which is a mere 4 or 5 miles tall. So you have a continent 4,000 miles wide, and the highest point is 4 miles. The continent's effectively flat as a board. And of course, it's wrapped onto the Earth. So if the continent flexes a little bit, flexes down, sea can come onto the continent. Flexes up, the sea goes off the continent. It's a process called uplift. 70 million years ago, a giant uplift forces the inland seas outward, emptying the continent. The retreating seas leave a rich mix of layered sediments in their wake. In time, this seabed will become America's Great Plains, an immense sweep of country reaching from Mexico, across Texas, up to Montana, and into Canada. Denver Museum of Science and Nature's curator, Kirk Johnson, specializes in the region. For 20 million years, this area wasn't a mile high, he says. It was 600 feet below the surface of the salty sea. Just go dig a hole in the Pierre Shale, and you'll find the teeth of 50-foot-long marine reptiles, giant fossil fish, ammonites, and meter-long clams. A whole host of things that really show you that there was a sea right here. Uplift drains the sea away from the interior plains. Further west, the same uplift triggers a different effect. The results are still visible today. The entire western interior of North America was flat as a board. Then about 69 million years ago, the Rocky Mountains pushed up. Most mountain belts are created on the margin of colliding plates. But the Colorado Rockies formed more than 600 miles away from the edge of the Pacific Plate. Some other force must have pushed them up. The subducting plate off the west coast of North America. Instead of going in and diving down, creating volcanoes right along the margin of North America, went in shallow, like a spatula under a pizza. Cracks in the crust allow granitic magma to escape the mantle. It rises to the surface and creates volcanoes. Today, there are 262 volcanic fields in North America. The majority of them have had little impact on the surface of the continent. There is one exception. It's called a supervolcano. Supervolcanoes leave enormous scars on the landscape scars that are visible today. This is a satellite view of the Snake River Plain. It's 400 miles long, a broad, flat depression that covers 1/4 of the state of Idaho. It's best known for its fertile agricultural land home of the famous Idaho potatoes. The land here contains a record of the North American plate's gradual movement over a stationary hotspot in the Earth's mantle. This hotspot produces a place on the Earth's surface that experiences active volcanism for long periods. Below the crust, abnormally hot mantle material wells upward. As North America drifts across this hotspot, it leaves unmistakable evidence of each eruption on the surface of the Earth. Today, the hotspot is directly under Yellowstone National Park. Eventually, the park's boundaries will pass over it. But for now, Yellowstone is the largest volcanic system in North America. Hank Hessler is the Yellowstone National Park geologist. Trying to imagine what the catastrophic eruptions look like is a challenge, he says. No human has ever witnessed these types of eruptions. But humans have recorded devastating eruptions in the past. May 18, 1980, Washington State. Mount St. Helens erupts with a total force of 24 megatons. That's almost 1,600 times as powerful as the bomb that destroyed Hiroshima. But compared to an eruption at Yellowstone 2 million years ago, Mount St. Helens is small change. Today, the caldera of the last eruption of this supervolcano forms the heart of Yellowstone National Park. Calderas appear when the magma chamber beneath the volcano empties after a large eruption. Fractures form around the edge of the chamber. They serve as vents. And as the magma chamber empties, the center of the volcano collapses. So much magma has erupted forcefully, forming volcanic ash, that the ground has actually subsided into a large hole. And this particular hole is about 45 miles long by 35 miles across. Yellowstone scientists have calculated that the eruption 2 million years ago ejected 588 cubic miles of volcanic material into the stratosphere. To put this in comparison, this is about 6,000 times larger than Mount St. Helens. What is 6,000 times larger than something, really? Well, many of us have spent $1,000 in our lives. 6,000 times larger than $1,000 is $6 million. And not many of us have spent $6 million in our life. A supervolcano belches millions of tons of sulfurous gases and ash particles into the atmosphere. This volcanic debris reflects the sun's rays, decreasing the amount of sunlight reaching the surface of the Earth, often triggering what's called a volcanic winter. Volcanic winters can drop global temperature by up to 9 degrees. Plummeting temperatures have also shaped modern North America. During much of the last billion years, the Earth has had no permanent ice. But cooling temperatures have occasionally helped cover much of the globe with immense ice sheets. These are ice ages. 200,000 years after an eruption at Yellowstone, the Earth enters an ice age. Boulder-studded glaciers advance and retreat over much of North America, carving and sculpting landscape. A university professor of geology, Charles McGarren, is an expert on glaciation. These boulders act like tools and actually gouge the Earth's surface and produce gouges and grooves on the orders of feet. It's like repeatedly dragging a cheese grater over cheese. Boulders embedded in glaciers gouge out grooves on the surface of the continent, over and over again. But it's the final polish of the Earth's surface, and the position of streams and creeks and valleys that was the product of glaciation. But the glaciers have another important effect. At the peak of the last ice age, so much water is trapped as ice on land that sea levels drop by as much as 450 feet. Huge new tracts of land are exposed. Today, you can stroll to the shoreline from New York's boardwalk in just a few minutes. During the last ice age, it would take days. During glacial periods, when sea level was down 50 to 100 meters, the walk was about 200 miles to get to the shoreline because the entire continental shelf of eastern North America was exposed during the last glacial episode. The Ice Age exposes so much land that America's coastline looks very different than it does today. Florida is around twice as wide as it is now. 300,000 years ago, the outline of North America as we know it today is trapped in ice. It's only when the glaciers finally melt that the true shape of the continent will emerge. 300,000 years ago, glaciers from the last great ice age are sculpting North America. Giant boulder-studded ice sheets gouge large chunks out of the earth. They create depressions in the landscape. When the ice melts, it pools. The most obvious effects of glacial melt back are the Great Lakes of the upper part of the United States, where enormous tracts terrain that have been sculpted by glacial ice were later filled in by the meltback of glacial ice sheets. North America's Great Lakes cover more than 94,000 square miles. They hold enough water to submerge the contiguous 48 states under 9.5 feet of water. They are the largest group of freshwater lakes on Earth, so big they are often described as inland seas. They emerged toward the end of the last ice age, when ice sheets many times the size of Texas recede. As ice sheets melt, water fills depressions in the landscape, creating millions of lakes. This is the most unique, Utah's Great Salt Lake. It's actually just a small remnant of a much larger ancient one. Lake Bonneville covered almost 20,000 square miles. Salt Lake City is built on its bed. The ancient lake existed from about 30,000 to 14,000 years ago. At more than 1,000 feet deep, Lake Bonneville was deeper than Lake Michigan. Professor Marjorie Chan of the University of Utah stands above Salt Lake City on the ancient shoreline of Lake Bonneville. She's been studying it for 6 years. We're on the ancient shoreline of Lake Bonneville. And about 15,000 years ago, at this elevation of 5,100 feet, the whole area and valley behind me would have been covered by a deep lake. Antelope Island and Stansbury Island would have been surrounded by fresh water, maybe with even fish, and perhaps even my toes would be in the water at the shores of Lake Bonneville. Fed by meltwater from retreating glaciers, the level of Lake Bonneville gradually rose. 15,500 years ago, the water reaches an elevation of about 5,000 feet, the lowest natural outlet for the basin. At Idaho's Red Rock Pass, the lake begins to spill over. The outflow of water begins to cut down into the rocks. Red Rock Pass weakens and then collapses, unplugging the lake and causing a catastrophic flood. 15 million cubic feet of water gush out of the lake every second, about 150 times greater than the flow at Niagara Falls. The amount of water that was rushing out would be the equivalent to, more than that goes through the Amazon River. Just huge amounts of water. And this is what we call the Great Flood. In about a year, the lake's level drops by almost 400 feet, releasing 380 cubic miles of water onto the Snake River Plain. The lake only stops emptying when the water level drops below the outlet at Red Rock Pass. The remaining water slowly begins to evaporate, leaving behind salt crystals. Over thousands of years, almost all of the lake disappears. Large salt flats mark its boundaries. Today, the Great Salt Lake is all that remains. The retreating glaciers of the last great ice age leave their mark all over North America. There's evidence in the most unexpected places. New York, America's famous city. Most of us associate it with skyscrapers, not glaciers. But New York's frozen geological past has shaped the city. Just 20,000 years ago, Manhattan and the Bronx were scoured by great plates of ice. Look past the joggers and workers enjoying their lunch break. And you can find plenty of evidence of glacial movement, even in Central Park. Dr. Charles McGarren can spot the signs a mile away. Picture a thick ice sheet, an ice sheet that is perhaps a mile thick. Think about the mass at the base of a mile-thick sheet of ice. Enormous pressures. And these enormous pressures literally pulverize rock. The rock formations in Central Park bear the scars of this pummeling. We're standing here right in the center of the large exposure of rock, much of which has been removed by a glacier. 20,000 years ago, New York is covered by a sheet of ice 5,000 feet thick. And you can picture how a 1-meter thick sheet of ice, with huge boulders embedded in the base of the ice, would have created this groove. The abrasive cycle of glacial advance and retreat even affects the city's design. It's amazing. Even the skyline of New York is dictated by geology. Turns out that tall buildings, which are the hallmark of New York City, must be rooted in solid rock. If you look at Manhattan, you recognize that the building heights actually oscillate from high buildings to low buildings, back to high buildings again. Why? Because in that area there's a very deep valley that's been sculpted by glacial ice and then backfilled with glacial sediment. Well, you just simply cannot build tall buildings in soft sediment. So the building height change in New York City is actually showing what the underlying geology is. North America's glacial period finally ends about 8,000 years ago. It has shaped the coastline of the continent and applied the finishing touches to the landscape. Glaciation has molded our cities and left behind great lakes, plains, and mountains. The continent we know today has finally arrived. This is continental North America. In the future, plate movement will rip the continent apart, just as it has time and again throughout its long past. It's happening today, right under our feet. This is the San Andreas Fault. It runs roughly 800 miles through California. It's the main boundary between the Pacific and North American tectonic plates. These two plates are moving in opposite directions to each other. The Pacific plate is moving northwest relative to the North American plate. California is being ripped apart 2 inches a year. At this rate, 1,000,000 years from now, California will separate from North America and become an island state like Hawaii. But that's not all. If we plot the projected movement of the Earth's plates over the next tens of millions of years, the face of the whole continent becomes unrecognizable. 50 million years from now, the Atlantic Ocean has widened. It has pushed New York away from Africa, moving the continent across Yellowstone's hotspot. Minnesota now sits on top of the supervolcano. 100 million years from now, California's Napa Valley and the San Francisco Bay Area have become Alaskan mountains. The Atlantic Ocean continues to widen. A subduction zone forms along its western shoreline. This zone will consume the Atlantic Ocean and set North America on a collision course with Europe and Africa. 200 million years from now, America's eastern seaboard no longer exists. North America and Europe collide to create a new supercontinent. Today's New York is now in the middle of a mountain range, once again at the center of a huge landmass, just as it was 500 million years ago. This may be our continent's future, but on a timescale that far outstrips our lifetimes. There are other changes, however, that mankind will witness. In the coming centuries, the North American continent may be a very different place. Much of Florida is underwater. The Big Apple is a modern-day Atlantis. It's an apocalyptic vision of North America's future, but it's us that's making it happen. For the first time in Earth's long history, the natural processes that forge the planet's continents are being influenced by man. Humans are very, very powerful geological agents. Look at the farm fields that stretch over hundreds of thousands and millions of acres. Look at the expansion of cities over many tens of square miles that have completely changed the landscape. By the end of this century, the population of the United States alone is set to double. To accommodate our ever-growing population, we're building new cities. Industrialization, our use of fossil fuels, and our continuing love affair with the automobile have sent carbon dioxide levels in the atmosphere soaring. Carbon dioxide traps heat inside Earth's atmosphere, increasing the greenhouse effect. The ice caps are melting and sea levels are beginning to rise. Jeremy Weiss is a global warming expert at the University of Arizona. He paints a gloomy picture of the future of North America. With global warming, there are certainly going to be winners and losers. The losers, however, are going to far outnumber the winners. Sea level rise associated with global warming will literally shrink North America. The shape of North America could change significantly, especially along the Gulf Coast and Atlantic coast of the United States. For example, the states of Louisiana, Florida, and North Carolina will see the greatest effects as far as loss of land to sea level rise. Minimizing or reversing these trends requires urgent action. In the short term, the next 100 or so years, the shape and character of continental North America will change. How dramatically is up to us. In the long term, we make no difference to nature's billion-year-old processes of growth and destruction. These are impossible to control. The awesome forces that created North America are still at work. We won't be around to see the results of these changes, but perhaps other generations will map their new continent and reveal evidence of our time, just as we have unearthed the story of North America so far.